this is another close look at interactions between objects. And there's some things in here that are kind of intentionally meant to be challenging for you guys. But it starts with a couple of questions. The first one is explain what a normal source is and give an example. This is going to be a force that is perpendicular to a surface. And it's kind of reserved for when things are in contact with each other. And it's always perpendicular. So hold on, Rn. So you can't have a normal force when things are not touching. So some examples might be if you've got a table and there's something sitting on the table, then you're going to have a normal force upward. It could be that you've got something that's on a slope. And you've got an object sitting on there, and then it's going to be perpendicular to that surface. You might even have two objects that are right next to each other. And so if, let's see, I'm going to draw a person. If this person is pushing on the wall, then in that case, normal force is going to be pushing back so that that person does not go through the wall. So it's always going to be perpendicular to the surface. Number 2 says, can an inanimate object such as a table exert a force? Sure it can. The only requirement for something to be able to exert a force really is that it has mass. Can the magnitude of the force exerted by an inanimate object change, explain, and give an example? What did you guys say? I'm just curious. Do you think it could change? Could you change the amount of force that you exerted on something? Yeah, how could you change it? So keep in mind that a force is equal to mass times acceleration. And so any change to the acceleration is going to change the force. So if one way to think about it is if you're pushing on something, like you can change the how much push you're applying, right? Usually that's by changing the velocity. We kind of usually think about it the other way. We think, well, I'm pushing it less, so the speed changes different. But that's all you got to do is change the amount of force there. Cars are another way to think about it, right? If you go from being a car moving at a constant speed, and you need to change speeds, that's going to change the amount of force you have. My car is dealing with a force problem right now called torque. Can't convert torque properly. But we'll straighten it out over Christmas break, I think. No. You guys think about car stuff too much? I don't know. I drove a stick when I was in high school, so I used to think about I think about them all the time. I know, my husband was dangling that in front of me. He's like, wouldn't you like a stick shift again? I don't know. I went to an automatic because I had children and I didn't want to deal with children freaking out in the car and a clutch at the same time. I know, right? Mm-hmm. So he's like, we could trade it in and get something with a clutch. And I was like, oh, that's interesting. But I think we're probably, going to do the safe adult thing. Fix the car that we have. Wait for good. Anyway, clutches are fun. Also, don't tell my mom this. Part of the reason why I got a clutch, I had my parents, they give you the old car when you're in high school. And then when I graduated college, I bought a Mustang, and I bought a manual on purpose because my mom and my sister cannot drive a car with a clutch. So it kept them out of my new car, which was definitely worth it. Anyway. That's like the most passive aggressive thing I've ever done. I'm going to buy a car that you cannot drive. All right. If the acceleration of an object is 0, are no forces acting on it? Explain. We've got this equation, right? Force equals mass times acceleration. If the acceleration is 0, are no forces acting on it? What do you guys think? It seems kind of implied, right? If this is 0, then this one has to be 0. But this works for an individual force. So if you've got a force diagram and you've got forces going in all directions, then what this really means is you have 0 net force, right? So this means that your net force equals 0 if so that may be true, right? Your net force is 0. Sorry, I'm going to make this 0 newtons. If your acceleration is 0 meters per second squared, but net force is the total of all forces. So you could have 10 newtons in this direction and minus 10 newtons in this direction and still have a net force that's equal to 0, but your object is still experiencing forces, right? You're sitting in a chair right now. You guys all look pretty peaceful right now. Like you guys look like you're not experiencing forces, but are you experiencing forces? You are, right? Because you guys are all sitting on a chair. So, if you're just an object that's sitting there, you're still experiencing gravity and you're experiencing normal force. And those things are true all the time. Almost all the time. Don't jump off of things. If you're jumping off of something, then you're not experiencing normal force. But generally, most of the time during the day, you guys are experiencing forces even if you're not accelerating. It just means that your forces are balanced. Does that make sense? Okay. All right, so then we did 4 and 5. So I was going to skip those unless you guys wanted to talk about them specifically. You guys want to talk about 4 and 5? There's a motion from the back from Maddie that no, we do not talk about 4 and 5. Okay. Should do Robert's Rules of Orders class. All opposed? Okay. Okay, so for number 6, how does the force that block A exerts on B compare to the force block B exerts on block A? We can answer that, right? We can answer that without even looking at the problem. Do you guys remember? This is a Newton's third law pair. For every action, there's an equal and opposite reaction. So the force that B exerts on A is equal to the force that A exerts on B. So we already know that much. So we know that they're equal. How do they compare? They're equal. Then draw and label a force diagram for each block using equality marks on the vectors. Okay, so for A is experiencing a push to the side, gravity, a normal force, and since it's moving at a constant acceleration, does this have to be balanced? This doesn't have to be balanced. Oh no. Not balanced means that forward is probably different than backward. So this right here is the push. This is B on A. This is this one right up here. There's probably friction or something. Something going backwards. For block B, we've got a forward, a push. And that's going to be by the finger on B, right? We've got a push backward on B by A. So this one is A to B. You've got a bigger gravity, got a bigger normal. All right. There might be some friction here too. For equality marks, we already said that this one is equal to this one, right? Two forces in opposite directions that are acting on two different objects. That's a Newton's third law pair. We know that it's not balanced, so that we don't really know about these two sideways forces. We don't know. But we do know that this one is equivalent to that, and those two are also equal and opposite. How'd you guys do? Okay. All right, number 7. Number 7 is tricky because there's a hook involved, right? So here we're pulling to the side. We've got a constant velocity. Constant velocity tells us that our forces are balanced. Because there's no acceleration. Excuse me. So we're going to have on B a force where the rope is pulling our block to the side. We also have a force here from this hook that's pulling block B in that direction. Do you guys see that? It's going to resist the motion of B. So this hook means that those things are going to be different than what they look like up here. So for B, we're still going to have gravity. We're going to have normal. We've got a pull from that rope. And we've got a pull from the hook. We know that all these forces are balanced, so normal and gravity should be balanced. They should be equal to each other. These two should be equal. Then if we take a look at block A is going to have gravity, normal. I guess we need to be consistent. Going to have normal gravity. It's going to have a pull this direction at the hook, and then some friction going backwards. So we've still got gravity, normal. It's probably friction. This one will have friction too. Here the hook is pulling A forward. And again, we're balanced, so these horizontal forces, the pull on the hook is the thing that connects these two. And that's going to be a Newton's third law pair. So this guy and this one, Newton's third law pair, those two. The pull on the hook from B on A is going to be the same as the pull on the hook on A from B. So those two have to be congruent. And then our vertical forces are congruent too. What questions do you guys have? How's this feeling? Okay? All right. Okay, these are where they get fun. We've got refrigerator magnet. You guys ever think about your fridge magnets? It's kind of magic, right? They just stay stuck there. So how does the force the magnet exerts on the fridge compare to the force the fridge exerts on the magnet? That's another Newton's third law pair. All right, next it says draw and label a force diagram for the magnet and the fridge using equality marks on the vector. So our refrigerator. If you've ever tried to move a refrigerator, it has a giant gravitational force, right? And your floor has to be pretty strong to hold it up. I always have an irrational fear that my fridge is going to fall through the floor. It's not, but they're very large. And we know that there's some interaction that's happening here with our fridge magnet, and our fridge magnet is going to have a much smaller gravitational force, right? Where's the normal force? Is the normal force upward with a fridge magnet? Yeah. It's got to be perpendicular to the surface. So here's gravity. Our normal force has got to be like this, right? So if we've got a normal force that's pointing away from the refrigerator, then we have to have something that's pulling it towards the fridge. What's pulling it towards the fridge? It's a magnet, right? So it's magnetic force. Let's write force mag because this is tiny. And then why doesn't it slide down the fridge? Kinda. So it's got a magnetic pull that's pulling it in. The reason it doesn't slide down is because it's got friction. We'll talk more about friction in January. It's crazy that's already December, but we'll talk about that in January. Now our fridge. If the force the magnet exerts on the fridge is equal to the force the fridge exerts on the magnet, our fridge has to be exerting some kind of force on our magnet here. Right? What is it called when our fridge is pushing against the magnet so the magnet doesn't fall through it? That's a normal force, right? So we've got a normal force that way. That doesn't look balanced though. It's got to be a sideways force. I'm reading on the name of it right now. I'm messing up the normal forces and the magnetic forces somehow. Oh, this one's got to be magnetic. And this one's got to be normal. That's what it is. So this one right here is the normal force on the fridge from the magnet. And then over here, yeah, this is the normal force on the magnet by the fridge. There we go. That makes more sense. All right, so those two are the normal forces, and those two are the magnetic forces. The magnetic forces are pulling them towards each other, and the normal forces are pushing outwards. How'd you guys do on those? The thing that's usually the trickiest is this normal force thing, and then recognizing that there's some friction. So I've got a magnet up on my board there that's holding that ruler up, and it can only hold it up because of friction. But the magnetic force has to also be strong enough that friction is enough. So when we talk about friction, that's going to make more sense. But you guys don't need to fully understand that right now. Do you guys have any questions about number 8? No. What are you guys doing today? Okay. It's a little weird. That's the last day before finals. My daughter had her last day yesterday, like until January, because they're going remote. So that was a little weird for her. Anyway. All right, so the next one, how does the force block A exerts on B compared to the force block B exerts on A? Equal and opposite. Okay. Here's the thing. If these things are falling, do they even exert forces on each other? What's happening here? If this was a single unit, how would we draw the force diagram? If it was just a single thing falling, the only thing we would have to draw here is gravity, because there's nothing that's holding it up, right? So if we draw them separately, and we've got A on the bottom, is A experiencing any forces from B? B's lighter. What if I take two objects and I hold them together and drop them? The one on the bottom did nothing to hold the one on the top up, did it? It's the same as if I drop them both. Same thing. So all that's happening here, A is just falling. Even though A is underneath it, A isn't exerting any forces on B. It can't. There's nothing supporting it. So all that's doing is falling too. These things are still equal and opposite. They're also equal to 0. 0 newtons. They're equal and opposite. They're both 0. How'd you guys do on that one? This is the same as our ball flying through the air problem. So when we're looking at those where we have, a ball and it's up in the air, the ball isn't in contact with anything. It's only interacting with the earth. So for this guy, all he has is gravity. That's it. All right. Number 10. How does the force that the earth exerts on a person compare to the force the person exerts on the earth? Again, these are equal and opposite. They're also not 0. That's a fun thing to think about, is that the earth exerts a force on you and it's strong enough to keep you from flying into space. A force that I am grateful for. I don't know about you guys. But I'm also exerting a force on the earth. It's just that I'm so small compared to the size of the earth. I don't think the earth ever notices. So when I draw a force diagram for the earth and for the person, for my person is experiencing gravity and normal force. If I'm looking at the earth, I'm going to draw the earth as a semicircle thing. If I'm looking at the earth is experiencing a gravitational force towards me, a tiny one, and a normal force downward. That's why the earth doesn't go through my feet. Another thing I'm grateful for. Can you imagine if you just got swallowed by the earth? Yay, normal force. I need better jokes for this unit, don't I? It's okay, Michael. Your eyes kind of look like you feel sorry for me for my terrible jokes today. All right, how'd you guys do on this one? This one's kind of an interesting one to think about, right? And then lastly, we've got the Earth and the Moon. Again, this is just gravitational force, and they're interacting with each other. But unlike number 10, they're not touching each other. If the Moon was touching the Earth, we would have other problems, right? So they're not actually touching each other. And so what we're going to see is that the Moon, this one's kind of easy, right? The Moon is experiencing gravitational force, so force of gravity on the Moon by the Earth. And this is the force that keeps the Moon from drifting off into space. It is drifting off into space, but very slowly. So this keeps it going around. And then because the Moon has mass too, the Moon has a gravitational pull on the Earth. So this is the force of gravity on the Earth by the Moon. Is that Newton's third law pair? It's two objects and it's their forces on each other. So these have to be equal to each other. So for equality marks, we put that one is equal to that one. This one, the force of gravity on Earth by the Moon creates major impacts on our oceans, and on the molten rock inside the Earth in the core, in the mantle. What's that called? The way that the Moon influences the Earth? Do you guys know? Starts with a T. Yeah.
Is it the tidal?
Yeah, it's our tides, right? And so the mass that the moon has pulls the Earth, the stuff that's on the Earth that's fluid towards it, which is really interesting. So it's a major component of plate tectonics too, because not just the liquids on top of the Earth are moving, the liquids that are inside the Earth are moving tidally too. This guy up here, if these two, so the Newton's third law pair are these two. And if there's no acceleration in either case, then these guys are going to be equal too. So they're all going to be balanced. Now, if our person here in our physics problem is jumping up and down, then that's going to create some issues too. Okay. So do you guys have any questions about those problems?